Sound, light, mirror, and lenses. Sound. Have you ever sat at a concert or a sporting event and just thought of all the sound around you? The sounds are all different, but they all have something in common. Each sound you hear is produced by an object that vibrates. For example, the friends that are sitting next to you singing along to the concert have vibrations that have been produced inside their vocal cords. Music coming from the speakers are also produced by vibrations from mechanisms inside the speakers. Now, when an object like a speaker vibrates, it collides with nearby molecules in the air, transferring some of its energy to them, and then these molecules collide with other molecules in the air and pass the energy onto them. This process of collisions and energy transfer form a sound wave. Sound waves are compressional waves, and we need to remember back to our chapter on waves that a compressional wave is made up of two types of regions called compressions and rarefactions. When air molecules are pushed together, it forms compressions, and when the molecules have room to spread out, rarefaction forms. As long as the object is vibrating back and forth, compressions and rarefactions are formed. When you get a series of compressions and rarefactions forming, they're going to travel from whatever is vibrating to your ear. And when it hits your ear, it vibrates the mechanisms in your ear. And the sound wave that you hear is what your brain interprets as sound. Now, most sounds you hear travel through air to reach your ears. However, you may notice if you're ever underwater in a swimming pool, for instance, that sound can also travel through water. And in fact, sound waves can even travel through solids. We need to remember that the matter that a wave travels through is called a medium. Now, depending on what the medium is, whether it's a solid, liquid, or gas, will determine the speed of the sound wave through which it's traveling. So, for example, sound can travel through air at 347 meters per second. Through water, sound will travel at 1,498 meters per second. And through a solid, such as maybe a large block of aluminum metal, let's say, it will travel at 4,877 meters per second. So sound actually travels the slowest in gases, a little bit faster in liquids, and the fastest in solids. So why is this? Well, solid molecules are closer together than molecules in gas. So when the molecules are close together, they can transmit energy from one another more rapidly. The speed of sound waves also depend on the temperature of the medium. We also know that as the temperature of a substance increases, its molecules will move faster. This will also make molecules more likely to collide with each other. When molecules are colliding more often, more energy can be transferred in a shorter amount of time. Therefore, the sound waves move faster. Now, when sound is coming at you, we just recently said that your ears and brain work together to turn those compressional waves caused by someone talking or maybe the music you're listening to another source, into something that has meaning. Now, making sense of these compressional waves come in 4 stages. The first stage is that the ear gathers compressional waves. Now, when you think of your ear, you probably mostly think of the part that is the fleshy part attached to the side of your head. This is the part of what is called the outer ear, or the visible part of your ear. The ear canal is also part of your outer ear, and your eardrum make up the outer ear as well. The outer ear is where sound waves are gathered, and in this process starts with the outer part of your ear, which is shaped to help capture and direct sound waves into your ear canal. The ear canal leads to your eardrum, which is a tough membrane about 1 millimeter thick. And then the incoming sound waves that reach this eardrum transfer their energy to it, and the eardrum starts to vibrate. When your eardrum vibrates, it passes the sound vibrations into the middle ear, where 3 tiny bones start to vibrate. These bones are called the hammer, the anvil, and the stirrup. They make a system that multiplies the force and pressure exerted by these sound waves, and they amplify these sound waves. Now, this amplification of sound waves is going to start vibrating the stirrup, which is connected to a tiny membrane called an oval window, which will start vibrating as well. When the oval window vibrates, the sound vibrations are transmitted into the inner ear, which contains the cochlea. The cochlea is a spiral-shaped structure that is filled with liquid and contains tiny sensitive hair cells. When these little hair cells begin to vibrate, nerve impulses are sent through your auditory nerve to the brain. The cochlea converts sound waves to nerve impulses, and these nerve impulses tell your brain to interpret the sound into what it is. I'm going to ask you to think back to our waves chapter and recall that the amount of energy a wave carries corresponds to its amplitude. For a compressional wave, amplitude is related to the density of the particles in the compressions and rarefactions. For a sound wave that carries less energy at a lower amplitude, particles in the medium are less compressed in the compression zone and less spread out in the rarefactions. For a sound wave that has higher amplitude, particles in the medium are more compressed in the compression zone and are more spread out at rarefactions. Now, imagine having your headphones in and you want to measure how much energy is passing from the sound waves to your ears. Intensity is that amount of energy that flows through a certain area in a specific amount of time. When you turn down the volume of your headphones, you reduce the energy carried by those sound waves, thereby reducing their intensity. Intensity influences how far away sound will travel because of some of the wave energy is converted to other forms of energy when it passes from particle to particle. Think about whispering to your friend. You have just created sound waves with a very low intensity, so they will not travel very far. Compare that to shouting to your friend across the room. Then the sound waves now have high intensity and can travel much further. When you hear different sounds, you do not need special equipment to know which sounds have greater intensity. Your ears and your brains are able to tell the difference, and this human perception of sound intensity is called loudness. Sound waves with high intensity carry more energy, and with high intensity sound waves reach your ears, they cause your eardrum to move back and forth a greater distance than sound waves of lower intensity do. As the intensity of a sound wave increases, the loudness of that sound you hear increases as well. Now, because people vary in their perceptions of loudness, a sound that seems fine to you may seem ear-splitting to a young child. So the intensity of sound can be described using a measurement scale. Each unit on a scale for sound intensity is called a decibel. On this scale, the faintest sound that most people hear is 0 decibels. Sound with intensity levels above 120 decibels may cause pain and permanent hearing loss. Another characteristic of sound waves that your brain interprets is pitch. You would hear a change in pitch, which is how high or how low a sound seems to be. The pitch of a sound is related to the frequency of the sound waves. Remember that frequency is a measure of how many wavelengths pass a particular point each second. Frequency is measured in hertz, which means 1 hertz equals 1 wavelength passing by in 1 second. When a sound wave with high in frequency hits your ears, your ear may have many compressions hitting your eardrum each second. A healthy human ear can hear sound waves with frequencies from about 20 hertz to 20,000 hertz. Most people can't hear sound frequencies above 20,000 hertz. These are called ultrasonic waves. Dogs can hear sounds with frequencies up to about 35,000 hertz, and bats can detect frequencies higher than 100,000 hertz. Infrasonic or subsonic waves have frequencies below 20 hertz, too low for most people to hear. These waves are produced by sources that vibrate slowly, such as earthquakes, wind, or even heavy machinery. Now, although you can't hear infrasonic waves, you may be able to feel them as a rumble inside your body. Let's take a break here, and it's time for you to show what you know.